So hello everyone. Today we will continue our lecture on firewalls. We have learned packet filtering firewall, and today we will move on to stateful packet inspection firewalls, shortly for SPI firewall. And before we heading to this new type of firewall, let's recap some essential points about packet filtering firewall, which are quite efficient and fast and transparent to users. So what it works, also you have done it in your assignment, is the packet filtering firewall. Basically, when it is placed in a network or in a computer locally, it inspects the header information of an incoming packet. More specifically, it will check some fields in the header of the packet, including the source IP address, destination IP address, the protocol number in the IP header, and also the source port number, destination port number in the TCP or UDP header. And these 5 elements will be compared with the rules in the firewall table, which will determine whether this incoming packet will be accepted or will be dropped. That's the idea of packet filtering firewalls, or the idea of firewalls in general. This process is rather efficient because it does not check the content of the application data, or we say the payload of the transport layer protocol. So it means if the traffic is allowed, it didn't change anything with the traffic flow, and it's transparent to the end system and end users. And there are 2 basic options to choosing this the policy of firewalls. We can choose default policy as accept, and then we add the rules in the firewall table, and then if the action in these rules would be either drop or reject. In this case, these kind of firewalls are more applicable to some more open systems, more open networks, maybe like the university network. But for some other systems and networks which are supposed to be more strict with the incoming traffic, then they usually set the default policy of the firewall as a drop and only allows certain traffic to come into the system. That's 2 options. If we want to have better security, better control of the network communication, then we should adopt the default policy as drop instead of as accept. So it's like the white list vs blacklist of the incoming traffic. So let's take a look at example of this packet filtering firewall to see. We have discussed previously for different examples with the default policy as accept, and we try to add rules with the action as a drop. Now we supposedly want to have a more secure control of the incoming traffic. then we want to have the default policy as drop. And we will consider to add some new traffic, new rules with action accept. So this is the topology that we have used before in Wednesday lecture. So we have 6 networks connected to each other, and we have 5 routers in between different sublets. And suppose we set a firewall at router A, like here, and now suppose we have a default policy as drop. And we want to allow some traffic. In this case, our aim is to allow the computer 12 in the sublet 1.1.1.0/24, like here, this computer, to visit websites in this subnet 3.3.3.0/24. And the computer is, or the administrator of the firewall is not clear about which computers in this network act as a web server. So it has to allow all the traffic to visit these subnets as a web browsing process. Now, let's see how can we add this rule to allow this type of traffic. So I had this file table in the screen, and we need to fill in what is the source IP address, destination IP address, what are the source port numbers and destination port numbers, and the action. So it's easy to see that the action will be accept. That's easy to see. I'll make it a little larger. Make sure you see the topology as well. Now, my question to you is, how can we write down the source IP address and the source port number? Can any of you answer this question and leave your answer at the chat? What should be the source IP address and source port number for this goal? Thanks, Marius. So we have source IP address as this computer 1.1.1.12. Then we use a colon to separate the source IP address and the source port number. Here, the port, because it's web browsing, and then we need to provide the port number for the web browsing. And is it correct we have the source port number as 80 or 443 in the source port number? Or should we change to the destination port number? Yes. In fact, because we were visiting the web server, so the destination port number is 80 for web browsing for HTTP. And if we use HTTPS, it's 443. So now we're clear about this destination port number. Now, what should be the source port number? Yes, the source port number here, because when the data is transmitted to the transport layer, the operating system will randomly generate a port number in this process to attach to this socket. And of course, the end user can manipulate this port number by some command, but in general, there's no need to specify the port number for general purpose. So say here, the source port number could be any value between 0 to 2 to the power 16 minus 1. That's a source port number. And what is the destination IP address? I think I need to move a little bit up to. What is the destination IP address in this rule or in this M? Okay, thanks, Marius. That's 3.3.3. That's here. Here I should write down at 24. Because it's not clear to the firewall here which is a web server in that network. So it has to include all the possible IP addresses. And then in this case, it's 3.3.3. This is one way to write all the possible IP addresses in this network. Another way is to directly write it as 3.3.3.0/24. So these two are exchangeable. So then now we move to the protocol. That's the protocol number. We can directly specify it in text. So it should be TCP because we want to have reliable connection between the client and the server. So this is one rule that we want to add it to the to this file table. Is that enough? What do you think? Is it sufficient to have just this one rule, and then the computer 12 will have a normal web browsing process? Will this computer receive some web pages from the web server? What star was? Georg, this star is called a wildcard. If it's written with a star, it means it can be freely chosen with these segments. Here, for example, for source port, the source port has 16 values, 16 bits in its field. When it's a star, it means this value can be any number between 0 to 2 to the power 16 minus 1. That's all the possible values in this range. And here, for this destination IP address, this wildcard, it's in the last segment, which has 8 bits. So it means that it covers all the possible values from 0 to 2 to the 255. That's 2 to the power 16 minus 2 to the power 8 minus 1. That's what this wildcard indicates. And my question to you now is it sufficient to have just this one rule in the file table such that the computer will have normal web browsing process. What do you think? No, yeah, with a question mark. Then what is missing? What do you think? Hans mentioned some websites use UDP as well. Yes, that's true. So we can add one more rule, like here. I use another color, like 1.1.1.12, then star or wildcard 3.3.3. Star, then 80 or 443, then UDP accept. Okay, then we have this new rule added to the file table. Is it enough? If we look at this rule, you see it's like the file here. There's a coming traffic from 12 to the router. That's the source IP address, and its destination IP address is in the network here. So when it comes then it allows this traffic, and then it allows forward this traffic to the to this network, and in fact it shouldn't go like this. It should like wire this router and here. What is missing in this rule? Marius mentioned it must be able to connect to the two subnets in between. Yes, suppose the other firewall, the other routers like router C and router D, they allows all traffic and it's already connected. And in this rule, you see the computer 12 send a packet. Suppose it's a HTTP request. Send this HTTP request within the TCP segments, then within the IP packet. Then it arrives at the router A. And the file will check, okay, the source IP address is correct, and the destination IP address, okay, matched with this rule, and it should allow. Then the file will allow this traffic, like to this network in the middle, the left middle one. And then router C and router D allows all the traffic goes to the subnet at the rightmost. So this is suppose this traffic get it through to the subnet 3 at the rightmost, right up. And what's the problem here? Then it's not just when we have communication, especially for this web browsing, it's not one-way communication. it should be two-way communication or bidirectional communication. Then what is missing in this case? Do you have some idea? What should we add further to enable computer 12 can receive some reply from that network? As I mentioned, this rule 1 in fact, this rule 1 is only for right here, only for the direction from. Yes, because we want to enable the 12, the computer 12 to have normal web browsing process. It means the computer 12 must be able to receive the replies from the web servers at that network, right? So in fact, we also need to have, I choose this one. Suppose it received this request and send back the reply. And the router should allow the reply from the network, right? And what is the source IP address and source port number in this rule? I write it rule 2. So here I will erase this part to add more information later. You can see TCP and UDP. That is correct. So we know we want to receive some reply from the web server, and we know the destination IP address is 1.1.1.12, and the destination port, it's not clear, and so we write star. And then we write the protocol, use TCP, suppose sometimes use UDP, I include it here as well, and we have accept. Now, what is the source IP address and the source port number in this example? Marius, the source port number is 80 or 443. Yes. And Peter, that's correct. The source IP address is 3.3.3. Then colon. No. Christopher asked why the port number is 80/443. To make it clear, maybe we write HTTP. It use the port number 80. HTTPS use port number 443. And because it's not clear which these two are the widely used port numbers for web browsing. So for the firewall, it's good to include both of them. Otherwise, it's rather hindrance to the computer 12 to visit web pages in that network. Is it clear now? So it's better to include both of them. That's correct. Now this is the process. You know, with rule 1, the traffic from 12 to the network 3.3.3.0/24 is allowed. With rule 2, then traffic from that network, one computer in that network, back to the router and to the computer 12 is allowed as well. So it seems it works as we expected, right? According to our major goal that allows the computer 12 to visit web servers at that network. Here I have a question to you. You may already seen it. A question is, this is the typical packet filtering firewall. And we want to have secure control. So we choose the default policy as drop. And in this example, we only add 2 rules in the file table to allow 12 to communicate a web server at the network 3.3.3.0/24. And here I have a question to you. Is there any way to bypass this policy? If there's, suppose now here, we suppose this 35 is a web server for normal web requesting and reply. Suppose this computer 36 is a malicious node or malicious computer. Is there any way that this computer 36 can bypass this firewall to send some data or some request to 12 with these 2 policies? What do you think? Or on the other hand, or maybe in other words, how 36 can send traffic to computer 12, even though it has these 2 rules in the firewall table? What do you think? Suppose you now what is the destination IP address in this case? Suppose it wants to send some data to this computer, and the destination port again, it's not clear, so it writes a star. And the protocol, again, suppose we use a TCP. Here, I shouldn't write here. It's better to, oops. I should add it below it. Suppose we have a packet from computer 36 So we have this is data, and this is TCP header, this is IP header. Suppose the source of the, maybe it's better to, it's, okay, I'll leave it. So here in the packet, the TCP, the source is and the destination is a star. Source, we leave it at the moment. And then IP address is 3.3. Source is 3.3.3.36. And destination is 1.1.1.12. So in order to make sure this packet can be allowed by the firewall rules in the table here, then what should be the source IP address in this IP packet? What do you think? That's true. Yes, that's true. Marius, in fact, here, if this computer 36 manipulate the data and manipulate the port number, which I mentioned before, that this port number, source port number, can be manipulated by the sender. If the computer change or assign the source port number as 80 or as 443 in its IP packet, then this packet will manage to go through the firewall policy, even we have this default policy is a drop. Right? Now you see this issue. Is there any way to prevent this issue? With how can we counter this type of issue? In fact, it's a type of attack if we consider more seriously, because it's a failure of the firewall. In one lecture, we mentioned the design goal of firewall is to make sure all the traffic going through the firewall and only authorized traffic can be allowed to the network. But now you see, even though we have very strict policy as drop by default, and we only add 2 rules for allowable traffic. But here, when there's an attacker in that network, destination network, And it's possible for the attacker to send traffic which will be managing to go through the firewall. So that's not a good news to security. If we check this IP packet according to the file rules in the table here, then the source IP address is okay 3.3.3.36. It's within this IP address range. And destination IP address is 1.1.1.12. It matches. Then source port number, destination port number, everything matches. Then the firewall will allow this traffic. How can we prevent this? Do you have some idea about it? Maris, it's not clear in this context. And also, in fact, for the IP address of web servers, it changes from time to time. Although when we type a URL in the address bar, we don't notice the change. But in fact, it could be changing at times. That's a good point. I see your point. You may want to say, what if we specify the IP address as 3.3.3.35? Then we can avoid some other computers to send this traffic that would be allowable by the firewall. Can we filter the data? What do you mean by filter the data? Or you can unmute yourself. That would be more convenient to explain your idea.
Can you hear me?
Yes, I can hear you.
So can we filter what data the computer at 36 can send to the computer 12?
You mean at the router A, right?
Yes.
That's doable, but not with a packet filtering firewall. And also, it's not quite clear to the firewall which computer's data from that network should be filtered or should be pay more attention to, right? It's not clear to the router or to the administrator when he or she set these filtering rules in the file table. Like it could be okay. Today is 36, and the other day is another computer from that network send out this traffic with a similar technique. Now you see the limitation of simple packet filtering firewalls in this example. It's not easy to just avoid this type of attack by simply adding more rules, right? It's even it's doable. Like if the 36 is suspicious, then the file tables would include all the other computers in the network. That's not quite efficient and convenient for the administrator who set up this file policy. Okay, that leads to our next firewall. That's called stateful packet inspection firewall. Do you need a break, by the way? Yes, we can have a 5-minute break, okay? Then we can continue. Is it fine? Yeah, if we start earlier, we could. Yes, yeah, Christopher. Let's say we have a rule. Christopher, it depends on the default policy. So you see, when we set up the firewall tables, the first thing is, what is the default policy? Is it accept by default, or is it drop by default? If it's by default accept in the file policy, then there's one way to specify the network traffic from 12 to the web server, and that we include it with action drop. But if by default the policy is dropped, then we don't need to specify this one. We don't need to include this traffic, which is supposed to be dropped anyway in the file table. Then in that case, the file table will only maintain the traffic flow that is supposed to be accept. Is it clear now? Okay, good. Now let's see, we restart at 1:30. So welcome back, everyone. Now let's look at the stateful packet inspection. Well, from previous example, you see the potential issue of packet filtering firewalls. In fact, this type of basic firewall makes decisions on individual packets. So we have these two rules. It only look at the file only looks at the head information, and then make decision. If there's another packet coming to the firewall, then the decision on these two packets will be independent of each other. That's what we consider this is the packet filtering firewall is called stateless firewalls. It didn't care about the state of that packet. It just look at the head information and make decision according to firewall rules. But in fact, for daily life, we have connections, we have communications from the client and the server, and some of these connections, they are related to each other. And it's useful to keep track of some of this relation to make more fine-grained firewall rules. So that's what the goal or the function of stateful packet inspection. So that's the idea of using stateful packet inspection. In today's firewalls, most of the software or tools provide this functionality to keep track of states of some packets that are related to each other. And in this case, if there's one original packet, that's the initial connection between the client and the server, is established, then all the subsequent traffic between the client and the server that is related to this original connection will be allowed. So it maintains two tables. One is the basic firewall table. The other one is in the state, in the packet state inspection table. It's like a complement to the packet filtering firewalls. That's the idea of stateful packet inspection. So the file itself maintains the firewall rules in the database. In addition to that, it also maintains the state information of the packet of the communication between the client and the server. So I think it's more convenient to look at the connection between the client and the server in more depth. Then you can understand this idea better. I will try to enter the full screen. Can you see the screen better? At least clearly? Okay, thanks. So here I wrote down this the essential points or idea of having stateful packet inspection firewalls. This type of firewall will utilize the relation between the current incoming packet and certain previous packet. And based on their relation, they will make decision about which action to take, whether it's to drop this incoming packet or whether to allow this incoming packet to the internal network. And these type of firewalls are mostly used for TCP connection. Now we look at a TCP connection, and you haven't learned this before, so I will go through it slowly. I don't like this. Okay. Again, we explain it through an example. Suppose we have a web client and we have web server. They want to have some communication. So the client wants to get some web pages or some files from the server. We make it simple, so we use HTTP instead of HTTPS. So then it has send request to the web server, and the server, when it receives this request, it will send back HTTP ARC or response. That's what we as end users experienced. But in fact, to have reliable communication between the client and the web server, there's some other process going on behind this. So in fact, when the web client sends some HTTP data, I just write data here. Before this data is encapsulated in TCP and then in IP, sent to the web server. In fact, the client machine will try to establish a session between the server. This session is this TCP session. previously, like this no connection, I will first remove the firewall here. So previous is a no connection between the client and the server, and both of them are in the idle states. And when the client machine receives this HTTP request from the HTTP protocol, it will first send a sync message to the server. This sync message is basically like, I want to talk to you. And the server, when it receives this sync message, if everything is in the normal state, then it will reply with sync and acknowledgement. In fact, originally it will reply acknowledgement, basically like, yes, I'm available. But it also needs to provide a state, like to sync. Here, sync stands for centralization. Synchronization is to keep the both sides at the same state with the data choke. This is a sequence number. And after it replies this, the server replies ACK acknowledgement. That's another number. ACK. It's acknowledgement. It also needs to receive data from the client. So that's why the server will also add this sync number to its packet. So to save time, to make it more efficient, then server replies both sync and acknowledgement to the client. And then the client, after receiving the sync from the server, it will reply acknowledgement. And you see it's a three-way direction communication. And it's this process is called three-way handshake. And this process is to establish the connection between the TCP client and TCP server. And in this case, it's the HTTP client and the HTTP server. And for this process, I write down this state. So when the client sends out this sync, it will keep the state as sync sent. And when the server receives the sync number from the client, it will load down, okay, sync received. That's the state update. And then the server will reply with a sync ACK. Meanwhile, it updates the state as sync ACK sent. Then after the client receives it, it will, here I should change it. It's a typer. So after the client receives, it will write received to update the state. And it will send this ACK back to the server. Meanwhile, it will update its state as ACK sent. So after these updates of states, then everything's fine. Then they will update the state as connection established. So with this, then the original application data will be encapsulated in the TCP segment and then encapsulated in the IP packet, then sent to the web server. When the web server receives this request, it will fetch the requested data and that encapsulated in TCP segment, further encapsulated in IP packet, then send back the data to the client. Then there will be a lot of traffic going in this process if the client maintains this connection. And at some time point, this connection will be inactive. Then the server will wait for a few seconds or a few minutes, depends on the configuration of the server. Then it will close this connection with the TCP client. And it will also send the message to the client, basically like, are you still active? I still want to talk to me. And if the client refuses to fetch more data from the server, it will just be quiet, and then it will update the state as timeout, and then close this connection. That is the TCP connection, the process of the TCP connection established and closed. That's the general process of this connection. Now let's look at what it matters for the firewall. Before that, I like to recap this process, the TCP header in the context of this the states updates. And you have seen this header before. Previously, we only used the source port number, the destination port number. In fact, in another field called flag, in this field, it keeps the information of this packet, whether it is the sync passage, whether it's the sync ACK passage, whether it is ACK passage. It's in fact, it's quite simple. This flag, you see, it has 8 bits for several fields. One field is for sync. One field is for ACK. By default, if everything is not related to the sync, then it will be this field, the bit value will be 0. If the client sends this sync message, then the sync field will be flipped as 1. Then the server will know, okay, this is a sync message. When it replies, then it will flip the both sync and acknowledgement field as 1. So it has 2 ones. It means sync and acknowledgement. And the client, when it sends this acknowledgement to the server, so it will flip the ACK field as 1, keep the other field as 0. Then it means it's a acknowledgement segment. That's how TCP controls or keeps track of the status update. So I got a question from Elas. So the first sync from the client asks if the server is available. Then the sync ACK from the server answers yes. But what does the last ACK from the? Okay, that's a good question. It's like to keep each side be ready for further communication. So the client asks, I want to talk to you. Then the server replies, yes, I'm available. I want to talk to you as well. then the client confirms that, yes, I'm ready to talk to you. So with this acknowledgement, it's like I'm ready to talk to the other side. Because there's a, so the flag, in fact, the flag has 8 bits. I only include the relevant bits. That's things you are asking. Let's take a closer look at the flag bits, flag field. Then you can get more. Can you see my browser? TCP header format. Let's see whether we can find the field information here. It seems so. One, two, three, four. It has several fields. You see its arc field, this is sync field, and this is urgent, this is finish. That's for the close connection. And there are some other fields. And each of these fields here, it takes 1 bit for itself. And there are some other reserved fields for future updates, let's say. So in total here, it has this 10, 16, here, excuse me, 6, and here it's a 6. So total it's 16 bits. So the flag information here is 6 bit. Sorry, I mentioned it's 8 bits, but I was wrong here, it's 6 bits. But mostly the other fields are not that important to communications. It's about the design of the TCP protocol. Okay, is there any question about TCP connection? No, let's move on to the previous case. Let's see how we can use a stateful packet inspection firewall to prevent the previous attack from the computer 36. Again, we have the similar setting. So suppose computer 12 wants to talk to the web server in this subnet, and computer 36 is an attacker. Now, in this case, when the computer 12 sends out some traffic, which is supposed to be sent to the subnet. And in this case, the source IP address will be 1.1.1.12, and the source port number is a star. It's the same, and the destination is 3.3.3. That's this here. Suppose it's we use this as well. Then destination, suppose we use only 80. Then we have port number TCP, and action is accept. So in addition to this rule in the table, in fact, it will maintain more information about the communication. So this is this SPI table. Suppose the original traffic when the IP packet from 12, so we write down the we have this packet. Although in the rules we have that the rule is okay, the destination IP address is 3.3.3 star, but in the IP packet it has to provide a specific IP address. And suppose it provides IP address of 35, and we have the IP address is the destination is 3.3.3.35. The source is 1.1.1.12, and the port star, source port, and the source destination port. So to make it simpler, I will just add here star and 80. And protocol, we have this TCP. So this extra state packet inspection table, SPI table, it will load it down here, this S, it will write include 1.1.1.12 star, and then 3.3.3.35 .80. The port number is TCP. Then originally, as we explained before the traffic, the real traffic, HTTP traffic between the client and the server. So the client will send this TCP connection request. So here, in the beginning, it will send this TCP sync request. Excuse me, to send the sync, this TCP request to the server. And during the communication between the TCP client and the TCP server, in fact, the router, in this case, it's a firewall, is always stay in between the client and the server, as we see in the topology. And it keeps tracks this status. So it loads when the client sends out this sync, then it will load down the state for this TCP connection is okay, sync set. When the TCP server replies with the sync ACK, it will update the sync ACK set. Because if it allows the traffic, then this status will be the computer will receive it, right? And then for the ACK here, again, it's when the TCP replies, the client replies this ACK, then firewall will update the state as ACK sent. It's like in the table here. So it will update in the beginning. It will be sync sent, and then it will be updated as sync ACK sent, and then will be updated as ACK sent, and then will be updated as established. So after this connection is established, so it includes the state as established in the SPI table. So it means if the web server 35 here receives this the HTTP request, it replies the HTTP the request according to the content of the data. Then the traffic will go back to the firewall. So in this case, the source IP will be 3.3.3.35 and then 80. That's the source IP and the port number. Destination is 1.1.1.12. So when the firewall receives this packet, it will check the SPI table first. Then it sees, okay, the connection is already established. The source IP address is this one. The destination IP address is 3.3.3.35. Then this reply from this the reply from this IP address is expected. So the firewall will allow the traffic going to the network. And if we have this computer 36, then suppose it sends the previous attacking packet 36.80 1.1.1.2 star. That's the source and the destination address for the packet from computer 36. When it arrives at the router A here, the router A will check this SPI table, and there's no match with the IP address, and the router knows this is not an established connection, and it is not related to any previous state or connection. Then it will drop this packet. That's the process of this stateful of using SPI table in addition to the previous packet filtering file table. That's the idea of using SPI table. Do you have any question? Maris mentioned why is the destination IP in the SPI table is, that's a good question. The key point of having SPI table is to keep track the established connection. It's not it's like this SPI table. So now you can distinguish the file table and this SPI table. The file table is more static. So originally it set these policy rules into the file table, added to the table. And then this SPI table is more dynamic. It keeps tracks the connection or the traffic in real time. So when originally the computer 12 sent out this request to the server, the computer knows the web server's IP address is .35, but the router doesn't necessarily know this. So the firewall in this case, it will load it down. First, in the original traffic, the router, the file will check whether this packet had information match the rule in the file table. In fact, it matches. then it will load down there's a one connection between this source IP address and this destination IP address in this packet, in this traffic, which is already allowed. And then for all the subsequent, all the later packets going through the firewall, it will update these states. But in this case, there's no way for the computer, for the device, to kind of hide some IP address information. Then it's like a ledger to load down the ongoing traffic's IP information and port information. And the firewall table is more static. Does it make sense to you? Okay, that's good. So keep in mind that this SPI table is more like it's an extra function in the firewall. It's a complement to the original packet filtering firewall, not necessary to replace it. Very good question from Ilas. With SPI table, when it writes down this source IP address, this source and destination, and when the state is established, then all the subsequent data traffic between the client and the server will be expected because of this established connection, and both direction will be allowed. So when here the source and the destination, the order can be changed, it's fine, and the firewall will always allow the traffic between these two IP addresses and port numbers based on this state. You can interpret it like that. You can think it as it adds automatically extra entry here. But for most of the implementation, they just add this one entry, one rule, then it allows both direction from this IP address to this IP address. Any more question? Okay, Marius mentioned, what if 36 also maintain a web server? Here again, the point is the computer itself knows the web server's IP address, but the administrator of the firewall policy, when they made the policy, added the policy into the file table, it's not necessarily to keep track the web servers in that network. So it only add this 3.3.3.star in the file table. In case, okay, at some point, the web server IP address is changed from 35 to 36, then if the computer 12, by some measure or for some reason, lose this update, so it will include this new IP address of the web server. Then here, the SPI table here will be the destination IP address will be 36 instead of 35. Then everything will be going similarly as we described before. Yes. Okay. Are there more questions about SPI? If there's no question, then I would like to wish you a nice weekend. And that's it. See you next Wednesday.